And I have to share, right?
Yeah. Okay, yeah, I think you should be all set.
Okay.
Okay, cool. Before we
if people on Zoom want, I can also turn on the camera, but I don't know. Maybe
honestly, I'm not even sure if people log on to the
Zoom. Then it's fine. Then it's fine. Because then otherwise, like if I move, it goes out or something.
Yeah.
Yeah.
I'm gonna run to the bathroom.
Sure. Yeah, no problem. Yeah. Hi. I'm Hi, nice to meet you. See you. I'm Mukul. I'm a postdoc at UCSD, San Diego.
I see. Great.
Yeah. I'm here for the seminar today.
I see. Yeah. Have you shared the screen?
Yes, I have.
Okay.
Yes.
Great.
So I've shared that screen. Yeah.
I think. Yep.
You're just eating raw cucumbers.
Actually, come to think of it, I've been getting the sister has to go to the seminar and they're like pulled out, pull like bell peppers and just like eat around the middle. If you can just like you left like a little bell pepper pit with the shit on his sleeve. So this is not but I might buy some bell peppers this weekend.
At least you're eating mess.
Well.
He was in the meeting. I don't know if he might be continuing that. So maybe we can just get started then.
Sure. Yeah.
Yeah, so today's speaker is Mukul. He did his PhD at Stony Brook, correct,
Yes.
and is now a postdoc at UC San Diego. He's been working on some like light dark matter detection experiments. So today he's going to tell us about something.
Sure. Yeah. Yeah. Thank you so much for the introduction, and thanks to Maxime for giving me this opportunity to talk here. It's great to be here. Yeah, so today I'm going to be talking about anharmonic effects in nuclear recoils, focusing on sub-GeV dark matter, especially on like this MeV to 10 MeV, 100 MeV dark matter mass scale. So this is a this is based on a very recent paper that we put on archive. So this is in collaboration with Tongyan Lin at UCSB, Chia-Hsien Shen, a former postdoc at UCSB, now a faculty in Taiwan, and Ethan Villarma, a graduate student at UCSB, who actually also just graduated. So just to get started, so this plot shows the current constraints that we have on dark matter nucleon cross sections in sort of this sub-GeV dark matter mass parameter space from various direct detection experiments looking for nuclear recoils. And you can see that we have constraints down to about 100 MeV dark matter masses. And the experiments that have put these constraints, especially in crystals, have reached thresholds of about 10 eV. So what this means is they can measure nuclear recoil energies down to 10 electron volts in their detectors. So of course we want to make progress beyond this point. And so one direction in making progress is probing lighter dark matter. So we want to go to the left in this plot. And to progress to the left, we need inputs from both, of course, the experiment and the theory. From the experimental side, we need detectors which have smaller thresholds, so which can read smaller energy deposits than the current thresholds that we have. So that also involves like building detectors with lesser noise, finding maybe new targets which have lesser band gaps, etc., etc. And from the theory side, of course, we need to calculate the dark matter scattering rates in this EV scale or even below that. On the theory side, we can also try to find new channels to probe dark matter nucleon interactions in this light dark matter parameter space. So one example that's been used quite a lot recently is, for example, the Migdal effect. So Migdal effect is when a dark matter comes in, hits a nucleus and scatters with the nucleus, but in that process, the atom actually has a prompt ionization, and you look for that ionization, but you're actually probing the dark matter nucleus interaction that happened initially. So that's called the Migdal effect. So one can look for like different channels to probe dark matter nucleon cross sections. We of course also want to go down, like we want to probe like weaker cross sections, weaker interactions on this in this parameter space. And for that, of course, the idea is we build bigger experiments, go to larger exposures, etc. But just that is not enough, because the detectors are typically contain backgrounds which limit your sensitivity. And so it's very important to understand, especially in these low threshold experiments, to understand where these backgrounds are coming from, and then devise and actually implement mitigation strategies. So these are all basically the active areas of research in direct detection and are being worked on. So in this seminar today, I'm going to be focusing on the calculation of nuclear recoil signals at this at sort of EV scale of energy, so below the current thresholds that we have, and even slightly below that. So that's going to be my main topic for today's seminar. So what's happening at what's so special that is happening at this EV scale? So this plot shows you an example of a potential that a nucleus sits in a crystal lattice. So when you're talking about a crystal and a lattice, the nucleus or an atom, it's not an independent particle. It sits in an ordered system. It's connected with each other. You can imagine them being connected by springs, for example. And the nucleus or the atom basically sits in a potential that roughly looks like this. And this is just some schematic potential that I'm showing here, roughly taking the parameters corresponding to a silicon lattice, for example. And then the thing to notice here is when you displace the atom by like an angstrom, which is the typical lattice spacing that you have, you reach potential energy of like roughly a few EV scales. So the idea here is that if your nuclear recoils deposit energies smaller than like roughly 10 EVs or a few EVs or even smaller than that, then you can't really treat the nucleus which is sitting at the bottom to be recoiling like a free particle. So the free elastic recoil prescription sort of starts failing if you deposit like smaller energies than these few EV recoil energy scale. So instead, the nucleus is basically going to oscillate in a very simple picture in this potential well. And because it's, of course, connected with other atoms in the lattice, is going to create some sort of collective excitation in the crystal. So, yeah. Oh, yeah. That's exactly what I'm going to. Yes, phonons. Yes, yeah. So these collective excitations, yeah, as you correctly pointed out. So these are exactly what are known as phonons in the crystals. So these phonons are basically eigen. So you can visualize them, or you can think of them as basically eigenstates or eigenmodes of these collective excitations of like a spring system of atoms in a lattice. So typically in a recoil process, you can excite just a single phonon through a scattering, or you can produce 2 phonons or 3 phonons, or you can produce multiple phonons. So you can produce basically any number of phonons here. And the idea in future experiments will be to exactly read off these phonons in your detectors. So there are already like proposals and ongoing work on like on experiments like, for example, SPICE, which will use target materials like sapphire or gallium arsenide, where the phonons will be produced. And then technology like transition edge sensors will basically read these phonons. And the idea is we want to reach sub-EV thresholds. So remember again, the current thresholds are 10 EV. So we want to reach sub-EV thresholds to read off these phonons. So yeah.
Working in like a liquid detector, say, where you don't have like a crystal lattice, is the threshold where you start to think about phonons is that particles that go lower threshold?
So there, I think, I mean, if you don't have a collective excitation in your system, so for example, you can think of like light noble liquids or light noble gases or something like that, then I think it's still an independent particle, like a elastic recoil, unless there are like effects like from maybe being a liquid or something like that. But if it's not a collective excitation, then you can think of it as an independent particle. But then you pay a penalty of like the mass gap between the dark matter and the nucleus that you are hitting. Like, because here you really want to probe like dark matter of mass scale like MeV or tens of MeV, where the nuclei you're talking about, if they are like GeV or tens of GeV or even 100 GeV, for example, xenon, then the nuclear recoil becomes inefficient at some point. Like the free elastic nuclear recoil becomes inefficient at some point. Okay. So there you would use maybe like lighter nuclei or something like that.
Like are these phonons gapless? The idea.
These phonons are, I mean, optical phonons have a gap. So there are both types of phonons that I think people could read out. So optical phonons, I think, have a gap. And acoustic phonons, the dispersion relation does go to 0. So I think they are gapless. Yeah, so you have both types of phonons depending on the material you have. Yeah. So the idea is, yeah, so to read off the phonons in these future experiments, and we of course now need to know, need to calculate signals at these EV scale parameter space or EV scale kinematic regime. So typically, if you look at the scattering rate calculations in the dark matter literature, especially for phonons, This scattering rate calculations are written in terms of this object, which is called as the dynamic structure factor. And the structure factor is basically just includes or it encodes all the information about your target, like all the gory details of like the phonon properties of the crystal, etc., etc. And that's the essential thing to calculate when you are calculating the scattering rate into phonons. So the scattering rate is written proportional to this structure factor S, which is a function of the momentum that the dark matter loses Q and the energy that it deposits omega into the crystal. And this is how the structure factor is defined. You don't need to look at all the details here, but the key quantity here is basically this matrix element of where you have this displacement operator e to the I q dot r. So r is the position of an atom in a unit cell located denoted by L. The atom itself in that unit cell is denoted by D. So that's how we are denoting a particular atom, and that's the position of that atom. So this is a displacement operator for that atom when you deposit momentum Q into that, and then you want to calculate its overlap between the ground state of the crystal Hamiltonian and some excited state that it goes to eventually of again an excited eigenstate of the crystal Hamiltonian. This F here is just some normalized coupling that the dark matter has with that particular atom. And then you sum up over all the atoms over this matrix element, and then takes the matrix element squared, allowing for potentially in general allowing for interferences between different atoms as well. And then you sum up over all the final states of the system of the crystal Hamiltonian, enforcing the energy conservation. If you're putting in energy omega, then the final state should have that energy omega. So that's the delta function in here. So that's how typically the structure factor is defined, but the key object is this matrix element here.
And the scattering cross section that you showed at the beginning, is that inside FLV?
Yes. So typically, I haven't included like the full scattering rate equation here, but there will be some like cross section with a proton or a nucleon inside. And this FLD is just some in units of that proton or nucleon cross section. You would say if a particular atom is interacting with matter or not. But yeah, FLD is basically denoting or including the information about the coupling of dark matter.
So again, L and D, what is the difference?
So that's just the notation here. So L is just like the denoting the unit cell in the lattice, and D is a particular atom in that unit cell. It's just a notation for denoting atoms in the lattice. So simply the crystal Hamiltonian, thinking very simply, is just the sum over the kinetic energies of various atoms, and then of course you have the lattice potential defined with respect to some 0-point energy or ground state energy of the lattice. And the potential energy of the lattice, you can basically again think of it like a spring system connected to each other, and you can define it or you can expand it in small displacements, which are denoted here by U, of different atoms on the lattice from their equilibrium positions. So the first term here is the very familiar harmonic term, what is called as the harmonic piece. So when we consider a perfectly harmonic spring, your potential energy that we know is like half kx squared. So that's exactly basically this first term here. So that's the harmonic potential, which contains quadratic pieces in displacements. But typically, your lattice is not perfectly harmonic. Your lattice Hamiltonian or lattice potential also has some anharmonic pieces. So those are like these cubic terms, and you can even have like higher order terms in displacements in your potential. So now, as I already mentioned, your scattering can produce any number of phonons. So starting from a single phonon production, 2 phonons production to multi-phonon production. So of course, the most fundamental process that's considered is a single phonon production. And the single phonon production has been studied quite a lot in dark matter scattering literature already. And it's seen that the single phonon production is a very dominant process, especially if you are considering low momentum transfers. So what I mean by low here is where momentum transfers are sort of smaller than the inverse lattice spacing. So when the momentum transfers are what is called in the first below zone, or roughly smaller than keV. For dark matter masses, it translates to dark matter mass smaller than MEP. So for these light dark matter masses and small momentum transfers, single phonon production is a hugely dominant process over any multi-phonon production. And as I said, it's been computed quite a lot in the literature. So typically it's been computed under harmonic approximation and using DFT methods in these references. So I'm just showing here one plot from one of these references. Again, don't need to look at all the lines here, but this is basically the sensitivity to dark matter nucleon cross sections that you can get if you can read single phonons in your detector. So this is again dark matter nucleon cross section on the y-axis and dark matter mass on the x-axis, and the solid lines here. So these curves. So different colors correspond to like different materials here, and these solid lines are basically assuming that you can read off energy depositions as small as 1 milli-eV. So you can basically read off like single phonons here. So phonon energies, a single phonon energy is typically milli-eV to like 100 milli-eV or something like that. So assuming that you get these amazing sensitivities if you can read off single phonons. But of course, there is a big caveat that you need to go to very, very low thresholds to actually read single phonons.
And what's this DFT? This is some field thing, effective field approximation is DFT.
Sorry, DFT is the density functional theory.
Yeah. So it's not this Zurich is doing this effective field.
Yes, I think yes. So Catherine has worked on. I don't know if it's this paper or I'll have to look at it again, but yes. So she has also worked on some effective field theories for dark matter couplings to phonons, etc. Yes.
So is that what you're going to use as well?
No, not really. Not really. I'm not going to talk about EFT or not even any DFT calculations. Like as I'll come to that point later. Like I'm just using a simplified picture in this work, but I'll go into more details.
Currently, correct me if I'm wrong, the law 180 election laws, the energy deposition is like enormous fragments.
Yes.
To get to that curve, you probably need like 10 orders of magnitude suppression to get to that curve.
Yes, there are absolutely tremendous amount of backgrounds. So not even actually 1 EV. So the current threshold is like 10 EV, and already like so below I would say 200 EV down to 10 EV, there is very sharp rise of backgrounds which are not completely known. So there is also ongoing research work about that. There are also hypotheses that it comes from like crystal cracking or something like that releases phonons. So maybe people can use like different glue techniques.
For me to understand, this thing becomes useful if we can mitigate this background.
Yes, absolutely. Absolutely. That's absolutely right. So I think these curves, it's not written on this plot, but I think these curves are assuming zero background. So these are like 3 events curves. Like
right now they have counting rates of like like kilohertz or something.
Yes.
Like that. And then you want to get to like 1 day.
Yes. So there is a tremendous amount of detector cleaning that is required. So again, as I said, even threshold wise and backgrounds wise, as you correctly pointed out, this is a like super optimistic and futuristic thing that I'm showing there. Is from this paper, I think by Zurich and company. But the point here is like if you can see, let's say, a single phonon, and let's say again you have zero backgrounds, very clean detectors, then you have amazing sensitivity. But again, you need these very low thresholds. So single phonon energy is typically max out at like 100 millieV. So even that is like 2 orders of magnitude improvement in the thresholds from the current thresholds. So this is going to be like super futuristic thing. So yeah.
When I go from 500 MeV down to a lower threshold of 120 MeV, why do I lose sensitivity?
So again, it's not written here, and it should have been written, I think, but this 500 millieV thing, it's not, so this is, I think, elastic. So this is a completely different channel. So this is a elastic recoil, and this is a single phonon. This is a single phonon. So you can see like the elastic recoil just completely stops at a point, and to go below that, like you have to basically rely on looking at inelastic excitation phonons or something like that. Yeah. So in the meantime, so one can think of this channel of looking for multi-phonons which offer higher energy. So you can have like EV scale thresholds and look for multi-phonons. For single phonons, you basically need to reach like about 100 millieV thresholds, for example. So that's one attractive alternative channel. So yeah. Yes. So it won't change the story. It's just that the for single phonons, it's like already 2 orders of magnitude improvement in threshold that you need. Multi-phonons, the good thing is it's maybe an order of magnitude or smaller threshold improvement, with which you can at least start seeing multi-phonons in your detector, of course, but it's going to be it's going to contain backgrounds if things are not mitigated. But I think people are working on that, and there are some hypotheses to like reduce backgrounds too. So in general, like computing this dynamic structure factor for multi-phonon excitations is a very hard calculation. The calculation that is typically done using DFT for single phonons that does not really scale well if you keep increasing the number of phonons. So this is a hard problem to tackle in general. So typically up to this point in the literature, what people have done is assume certain approximations, like work in certain kinematic regimes, and then that sort of simplifies the analysis, and then tackle this problem analytically in a particular kinematic regime, and so on. So one such approximation, so that was considered in this paper, is what is called as a long wavelength approximation, where it was assumed that, let's say, the momentum transfer is smaller than the inverse lattice spacing, and then they can somehow simplify the calculations a little bit and calculate analytically what this dynamic structure factor is. And there they actually calculated 2 phonon scattering rate. The other regime is like Q bigger than Q bigger than sort of this inverse lattice spacing that you have. So here one can use what is typically called as the incoherent approximation. So what this incoherent approximation means is that basically you can neglect interferences between different atoms when you calculate the structure factor. The intuition behind this is that when your momentum transfer is higher than like the typical inverse lattice spacing, then your momentum transfer is big, and the inverse Fourier space, you're basically focusing on one atom, and your momentum transfer cannot resolve basically interferences between different atoms. And if you remember in the dynamic structure factor, there was a sum over atoms in the matrix element. Before taking the matrix element squared, you can basically take the sum afterwards and neglect the interferences between different atoms. So that's the help that we get by making this approximation. So within this approximation and considering the harmonic lattice, this reference calculated dynamic structure factor for multi-phonons for any number of phonons, and they found a nice analytic expression that one can use for a particular number of phonons. But the important point to note here is that a harmonic crystal was assumed in that calculation. Now, in this older reference, which calculated a 2 phonon scattering amplitude, They found large, so they actually did include anharmonicities in their crystals using some effective elasticity theory. And they found pretty large anharmonic corrections that you can get for two-phonon scattering in this small momentum transfer regime. So the natural question is what's happening in this regime where the momentum transfers are higher, let's say, than the inverse lattice spacing. How would the anharmonic effects basically correct the rates that were calculated in this paper? So the intuition behind this is, okay, so at low momentum transfers, they found anharmonic corrections that can be as big as the harmonic contributions to the two-phonon scattering process. If you go to extremely high momentum transfers, let's say much bigger than the inverse lattice spacing or anything, where you sort of start recovering your free elastic recoil regime, like very hard recoil, then you don't expect any anharmonic corrections, because if your nucleus is getting a hard recoil, then it's not going to care what shape of the potential it's sitting in, basically. So in low momentum transfers, they saw large corrections, and in very large momentum transfers, we don't expect to see any anharmonic corrections at all. So the question is, in the sort of intermediate regime, what's happening with these anharmonic corrections? So that's sort of the question that we try to answer in this work. Again, we are working under the incoherent approximation. So this momentum regime. And further, to simplify things, so I'll talk about this pretty soon. But we'll consider a simple 1D picture of an atom. So just one atom basically sitting in a one-dimensional potential, and we'll include anharmonic corrections to that potential.
When I'm trying to detect these multi-phonon events, like if I see two phonons, how do I actually know that they came from the same event? Do I have like directionality?
That's a good question. You could have a directionality. But I think in your detectors you just have some time. What can you say? Time.
I would think is extremely difficult. I think this whole point of this transition edge sensors and so on, when they use a small point of contact, and then
Yes.
this excitation bounce around.
Yes.
Before they get absorbed. So I don't think it's going to be like you just the phonon flies away and you detect it right away. This is like a lot of motion inside the ball.
That's true. Yeah. So I'm not actually completely sure if you can really tag a particular thing to a particular event, like the energy deposition that you see to a particular event. Like, of course, they have some timing resolution, but yeah, as you correctly said, like typically the transition edge sensors are placed on one surface, and they I think occupy a small area, and the phonon could be created anywhere. It's possible that it could decay as well, and then it can bounce around and sort of at some point get absorbed. So I don't think it's an obvious thing that it will that you can attach it to a particular event or something.
Okay, so if I see something, I don't know if it's coming from like this calculation or just it was like the calculation for my single photon event might have been wrong, but maybe I just get more single photon events.
Yeah, it could be. Yes, that's a good question. Yes, that's a good question. So I think in the detectors you would see just the energy deposition. I mean, because it's in the end it's like a fancy calorimeter. Basically, it's like reading energy deposition, and you get some time reading, like at what time, basically at what energy was deposited, etc. But yes, that's a good question. Like you won't be able to say if let's say you measured like 100 single phone. I think that's your question, right? Like 100 single phonons, or like 100 phonon event, or something like that.
Yeah.
That maybe your questions. Yeah, I'm not sure if you can really distinguish that. Yeah.
Sorry, can I just ask?
Yeah.
Just to get a sense of scale, so like
Yes.
this long wavelength where they were seeing that this anharmonic in the two phonon. How much longer do you have to go till like only single phonon is the dominant thing?
Oh, single phonon is already the dominant thing here, actually. like as soon as you go below keV, like single phonon is already the dominant process, but they just calculated the 2-phonon scattering as well. Like it's not like you can
Like,
just
is there
produce
some,
single phonon.
is there some like sufficiently small momentum where, I mean, it seems like they found like this interesting correction for 2-phonon in a
Yes.
regime that was, okay, that was already sort of the single phonon dominated.
Yes.
But was this correction like order 1 to the single phonon rate, or was it still?
No. It's not order 1 to the single phonon rate. It's like order 1 to the 2-phonon harmonic rate.
Okay.
Yeah, so it's
Sorry,
not-
okay,
yes,
but it's
yeah.
still, okay, sorry.
No, that I think that's an important point. Like so it's comparing basically 2-phonon harmonic versus
Yeah.
2-phonon
Okay.
anharmonic. Single phonon is absolutely, like, I think by a few orders of magnitude
okay.
still.
Yeah, I was confused.
They're
when you said
dom-
long.
Yeah, sure.
Okay.
Yes. Yeah, so basically in this work, we consider a very simple analytic toy model to simplify things and try to include anharmonicities. So what we consider is a 1D, just simple 1D case of an atom. And we again work in this incoherent approximation that I talked about, where you neglect the interferences. So the structure factor then can be simplified into this expression, where the sum over atoms is now outside. You basically, the key element to compute is this matrix element. Now it's in 1D e to the IQX, and you are basically computing the overlap between some ground state eigenstate to a final eigenstate of the one-dimensional potential of an atom, just the kinetic energy plus some potential. So now, of course, we need some validation that this 1D approximation, that you're basically neglecting like the other directions and sort of simplifying with a 1D picture. We need some validation that this works. So one thing that we tried to do was just use, first of all, before going to the anharmonicities, just work in the same picture of a harmonic thing. So just consider a harmonic potential in the place of this V, and take some typical phonon energy that we see for this omega 0, and take half m omega square x square as this potential. So now if you do that, then if you do that, then this is just a very simple typical harmonic oscillator problem in quantum mechanics, and the initial and the final eigenstates are again the simple harmonic oscillator eigenstates that we know from quantum mechanics. And then we can basically compute this matrix element squared, or this overlap, using very simple like ladder operator algebra. And what we find is that this matrix element squared basically goes as something like this. So this is something proportional to this. I'm dropping like some numerical and combinatorial factors here, but it goes something like this. So we see that the first factor in this expression is like q square over 2m omega. M is the mass of the atom. Omega is the typical phonon energy. So this gives sort of a natural scale in the problem for the momentum transfer. So q squared is compared to 2m omega here, and this is to the power of n for going to the nth excited state, and then you have the exponential suppression of the same factor essentially. So the interesting thing is this reproduces, so this behavior basically reproduces the behavior of the structure factor that was found in the case of harmonic, like full crystal calculation that was done in the incoherent calculation, in the incoherent approximation. So this actually matches completely, this behavior matches with the structure factor for creating n phonons in a harmonic crystal. So going from the 0 to nth excited state for a 1D potential actually corresponds to creating n phonons in a harmonic crystal. Except, so one caveat here is that you of course don't reproduce like the phonon spectrum that you actually have in a crystal. Like you don't have a single phonon energy, but you have multiple phonon energies that you can get. There is a band and something like that. So you have a phonon spectrum, but here you're just considering like this single energy, and you get this delta function. So the only difference that the only change you really have to make is basically substitute this delta function by some by some smudging of the spectrum. But I won't really go into the details of those things, which we talk about a little in some detail in the paper. But the essential thing is it basically reproduces this this structure factor, and it sort of gives us a natural scale and a dimensionless factor of q square over 2m omega, in which basically you can expand the number of phonons. So if this dimensionless factor is much smaller than 1, so this 2m, so the square root 2m omega is basically order 10 keV-ish. So if the Q is much smaller than that, like 10 keV or 50 keV, so we are talking about in the incoherent approximation, we have a lower cutoff of like keV. So in between a keV and 10-ish keV or 50 keV, then you can basically neglect this this exponential piece and basically just expand in the number of phonons in the exponent here. And then as you keep increasing Q, when this dimensionless factor becomes closer to 1, then sort of you have to take into account multiple phonons and large number of phonons. So this expression basically has to be summed up because then this factor to the n basically starts mattering for high n. And then if you even go to higher and higher Q, you basically sum up over all the phonons and you analytically actually recover your free elastic recoil picture. So that's roughly the idea of this dimensionless factor that we will encounter in the anharmonic calculation as well.
And by the way, the fact that it reproduces the structure factor in the more like complete crystal calculation, yes. The intuition for this is based on what you had said about like I forget what you call it, but it's like the incoherent limit where you kind of are treating each atom as
yes.
impacting others.
Yes.
So it kind of makes sense, right?
Yeah, so there is that intuition that when your momentum transfer is high enough, then you are basically focusing on a single atom and what it's doing. It's still mysterious, at least to me, that the nth excited state of that just one potential well actually corresponds to like n number of phonon, like n phonon, because phonon is like a collective excitation still. So it's still kind of a coincidence actually for me, but there is that intuition, definitely there is that intuition. But you can maybe think of it as some sort of a factorization process, like you are because you are in this high momentum regime, you are exciting first that atom to some excited state, and then that sort of is giving away its energy in the phonons, in the that sort of a long time scale picture. Yeah, but this behavior is like completely reproduces that full crystal calculation. So now.
So this is known.
Yes, that is completely true. So many of these things, so I don't know exactly which ones and to what extent, but that's absolutely true. So like many of these things are like borrowed from like neutron scattering literature, where they have computed this. I think even the definition of structure factor and things like that in the earlier dark matter references that I showed, I think they have been borrowed from the neutron scattering literature. Yes, that is true. But at least like as far as I know, like these things have been pointed out for the first time in like dark matter scattering literature. But yes, they're there in the neutron scattering literature, maybe in a different language, but yeah. So the idea here is to treat the same problem, but now include the anharmonicities. So typical atomic potential is anharmonic. So on the right hand plot, I'm showing the potential of a silicon atom when it is moved in like different directions from its equilibrium position. So these potentials we actually computed ourselves by modeling interatomic forces on the lattice and just moving the atom in one of the directions. So you see the black line here is the harmonic potential. So you see that in some direction maybe it matches the harmonic, but in other directions the potential has some anharmonicity in it, and then when we try to fit these anharmonic potentials to a harmonic term plus some higher order terms in X or the displacement, then we find that the anharmonicity is dominated by cubic and quartic terms mainly. So in this work, we basically consider a harmonic potential plus a cubic potential and a quartic potential. So a potential of this form for an atom.
Wait, so each of
Yeah.
those curves, when you move in different in a different direction,
Yes.
so does it make sense to be talking about this as a 1D potential, or shouldn't I really be talking about it as a 3D?
It is. Yes, it is. It is in the end, like if you want to do a complete calculation, it is a 3D thing. Like you need to take into account, like depending on in what direction the atom is getting scattered, you need to basically take that anharmonicity into account. But we are sort of doing a very simple thing here, and what we are doing is we see we see a direction which has like a maximum anharmonicity, and we treat as if that anharmonicity is almost everywhere in all the directions. So that sort of sets like a maximum effect of anharmonicity. So the actual effect is going to be smaller than that. So it's so there are of course going to be some order one effects. Yes. But yeah, the actual problem is a 3D problem because as you pointed out, it's not an isotropic thing.
Okay, you're trying to like bound the amount.
Exactly. We're trying to bound or trying to at least get a order one estimate of what the effect, like how much the effect can be and in what parameter space the effect is basically. Yes. Yeah, so the aim as we did the harmonic, as we saw the harmonic calculation, the aim is to compute eigenstates of this anharmonic potential. And again, just compute this matrix element squared. We just compute this matrix element for a ground state of this perturbed Hamiltonian or anharmonic Hamiltonian to some excited state n, where the dark matter is basically exciting it too. So we take two approaches here, like one an analytic approach, and other is just a numeric computation of the eigenstates. So I'll talk a little bit in the time that is remaining about both. So in the analytic approach, we use a perturbation theory picture. So what we do is we treat these λ3 and λ4, which are the parameters which control the anharmonicity, as like small perturbations over the harmonic piece. And we also work in this regime of Q smaller than this natural scale that I talked about, square root 2m omega. So that dimensionless factor that I talked about, that being smaller than 1. So you can also expand in that parameter. I'll show the analytic results soon. So if we,
It seems like this
Yeah.
would be an exercise.
yes, it is, yeah. It is, yeah. yes, absolutely, it is, yeah.
The complications that we've got.
We are doing it on lattice. So yes, I mean the actual scattering rate is going to be complicated because of two things. So one is, I think what he also pointed out, that is going to be like an anisotropic thing. And also the other thing that I talked about was it's just not like a single frequency or a single potential that the atom has, but there is like a spectrum of phonon energies that you sort of have to take into account in the end. So there are a few complications that arise going from this very simple picture to an actual crystal. But yeah, just this is a nice exercise in quantum mechanics, basically. Yeah.
By the way, also this Q less than root 2m omega.
Yes.
This is also corresponding to like a sort of small phonon limit, right? At least in the sense that you have this identification between the nth eigenstate and in phonons.
Absolutely, yes.
This is kind of like order few phonons or something.
Exactly. So I mean the idea here is, yes, so you can basically expand in like the number of phonons, because in the harmonic picture we saw that this dimensionless parameter Q over this thing, the harmonic scattering rate just goes as 2n, like this factor over 2n. But yeah, as you go to higher, then you have to like sum up, take into account the other exponential that was there, and so on.
And if I expand this exponential in Q, this would correspond to the cylinder strength or whatever it is.
Yeah, it's I think called like the Debye-Waller.
Right.
Fact.
And
Yes,
it's good to look at.
yes.
So this would probably relate to some, I don't know, line lengths with or some bulk.
Yes, I think so. Yeah. So in this limit, it would be 1 basically, like that exponential would be roughly 1. But yeah, if you go to higher Q, I think you have to
If I approximate exponential by 1, then I have this whole matrix on is 0 because by 0 and by n have all
yes, sorry, you're talking about this exponential. Oh, sorry. Okay. I thought you were talking about the exponential with the Q to the 2n that was appearing. Okay, sorry. Yes, this exponential. Yes. Yeah, that's true. Yeah.
So if that, because you find some out of a long way limit, right? This will correspond to some matrix element of X.
Yes. You can right. You can do like
this is an order.
Yes. Okay, yeah, you can do like QX, like Q would come out and you're basically just taking the element, like matrix element of X, the operator X between the two states, etc. Yes.
And then you only get the first excited, which is like the one photon.
Well, for harmonic.
Exactly. Yes, for the
I
harmonic.
only know
Yes.
maybe.
Yes. Yeah, that's exactly what we are going to see, like what the anharmonicity basically does.
And to be clear, you're calculating the transition from the ground state to the nth excited state, and you're just assuming that corresponds to the scattering rate to n phonon.
Yes.
Because that's what you saw in the harmonic.
In the harmonic
You
case.
don't
Yes.
know that's necessarily true.
There is no really calculation to, I think, really validate that or compare to. But I think in this limit, that's a fair assumption, seeing what we are seeing for like seeing the analytic expressions for the harmonic case. Yes. But yeah, that's what so what you said. So that's what the perturbation theory does if you include like anharmonic terms. So okay, so let's say we just take a cubic perturbation, like the harmonic term plus some cubic, like a lambda 3x cube term in the potential. Then let's say you want to calculate the perturbed zeroth eigenstate. Then you start from the simple harmonic oscillator state 0. Then from parity of the x cube term, at the first order you get mixing with 1 and 3. The second order you get even states, etc. And you can just keep going at higher orders in lambda 3. You can play similar game for the nth excited state, starting from the unperturbed state and basically expanding in different orders of lambda 3. Again, I'm just showing a very simple schematic picture here and dropping like all the numeric factors in front, which can be important in some cases. So what this does now, when you try to compute the matrix element overlap between these two, is so first at 0th order in lambda, you're basically taking overlap between this and this. So that recovers your harmonic piece, which we saw was like this dimensionless factor to the n for the n phonon scattering. So that's just the harmonic thing. And now at different orders in lambda 3, you get like mixing between these two expressions. So we see that at order lambda 3 squared, you get this dimensionless factor to the n minus 6 and then increasing in 2. So crucially, actually, you can see the power it drops by 6 here, like the leading order. Then if you go higher order in lambda 3, then you get even smaller power that you have accessible here. And you sort of see this whole pattern. You can, because we're working in this limit, you can basically expand here like that. And you're also assuming that lambda 3 is small. So you can expand at different orders in lambda 3. So taking just some few simple examples. So for a one phonon case, the harmonic piece is basically this dimensionless factor to the power of 1. And the anharmonic is also the same factor because you don't really have a q to the 0 piece because of orthogonality. And that is suppressed by lambda 3 squared. So for one phonon, the dominant piece, when you look at q smaller than the scale, is always going to be the harmonic thing. So for one phonon, the anharmonic pieces are always going to be suppressed by these small lambda 3 terms. But the situation is different for a two phonon. So you have this harmonic piece where it's the dimensionless factor to the square. And on the other hand, you have this dimensionless factor to the 1 at some order in lambda 3, like here lambda 3 square, basically. So what you can think about is if you go to small enough q, where the dimensionless factor is smaller than 1, then this term starts dominating this term at some point.
Yes. So can I rephrase that harmonic oscillator has additional selection rules
Yes.
that are
Yes.
in fact suppress the effect.
Yes.
undo
Yes. 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 And at some point you can sort of overcome this separation of lambda if you keep going to smaller q, and then this term can basically dominate or be at least of the same order as your harmonic piece. And then you sort of start recovering the result that was seen in the small momentum calculation. And there is a same story for three phonons, and you can continue looking at higher phonons, etc.
In order to maintain the incoherent approximation, you said Q needs to be bigger than like a kV.
Yes, that is true. So
it's like 10 kV. So
ratio is order 10 kV, like 15 kV or something like that. Typically, for example, for silicon, I think this is like 50 kV. So I agree. Like there is a small window in which you can really apply this calculation. Like I think at most a couple of orders of magnitude. So that's why I said like this calculation is most suitable for like dark matter masses of like MeV to 10 MeV ish scale. Below that, you really have to rely on the long wavelength calculation, and you do already expect the anharmonic effects to be big. But is the in between thing where we wanted to see how it at least goes to sort of anharmonic dominated regime.
But so this ratio Q over QM,
Yes.
that ratio is like at worst like 0.1 or something.
Yes.
How big do you expect the anharmonicities to be?
Yes. I'll show a plot like how it basically goes. Yes. Okay. It can go to like an order of magnitude or even 2 orders of magnitude. Yeah.
So,
yeah.
I was wondering, these corruption terms, can you also get them by this form of this naive dimensional analysis? You see, you can give a dimension to the coupling, you can actually probably it's an expansion of H bar.
Yes, I think so, but I'm not sure like if that would give you like a stopping point at a particular lambda. Like for example, for an n phonon harmonic case, you have a term which is q to the 2n, and then at a particular order in lambda, you can go down to a particular point. Like for example, you see you can, yeah, like this is not a good example to see that, but like if you are, for example, at like 6 phonon, then it's like q to the 12, and then at lambda 3 squared, you can go to q to the 6, but not below. So that's I'm not sure if that would.
Okay, but that's more information.
Right. Yes, but
Naive dimensional analysis, we know about that, but it will tell you the structure of all of this.
probably, yeah, that's a good point. Yeah.
This is used in field theory. I mean, I don't know if there's probably an effective field theory here for the photon coupling, and you could probably get the same structure.
Probably, yeah, that's possible. That's a good point. Yeah, I haven't thought about like from.
It's used in trial derivation theory.
Okay. Yeah. Okay. Yeah. That would be a good point to look at. Okay. I see. Okay. Okay.
dimension for coupling plus H bar.
Okay.
Two together.
Okay.
Actually, wasn't there some paper maybe a year or two ago out of the Florida group that had some effective field theory of multi-phonon stuff? I don't remember. That was specific to the superfluid helium though. I think.
Yes,
I
yes,
don't know.
that was superfluid helium. Yes.
Yeah, I mean,
Yeah.
at the end of the day, it might not give you any more information. I was just wondering, that's all.
Yeah. No, that's a good. Yes. That.
That's
Yeah. I think that's a good point. Like worth looking at. Yes. Yes. I agree. Yeah. Thanks for that. Yeah. So yeah. Okay. In the interest of time, I'll go pretty quickly. Okay. So the takeaway from the perturbation theory is basically anharmonicity can dominate if you go to low enough Q, and these are the terms basically that are giving you in the structure factor that are giving you this this enhancement. I'll then maybe skip over, like you cannot really use perturbation. You cannot just continue using perturbation theory because of a few reasons. Like first of all, it's also impractical and a little messy to calculate, taking into account all the terms. And it also starts failing at high N because the corrections that you start seeing for higher number of phonons, at some point, you cannot really treat this lambda 3, lambda 4 as a perturbation. So that's why we resort to like taking a numerical approach. So here we just do brute force, like just take this potential, fit lambda 3 and lambda 4 to a direction of maximum anharmonicity, and just directly compute, like literally discretizing the Schrodinger equation and just solving it and computing this overlap square. So that's just the brute force numeric approach that we also take. And then in the last minute or so, I'll just quickly show you the results. So similar to the intuition that we got from perturbation theory, the structure factor here is shown as a function of as a function of Q here. So as you correctly pointed out, like this is roughly the scale of that square root 2 omega, roughly 50 keV, and this is like a stopping point of the incoherent approximation, because below that, then you have to take into account like interferences between different atoms. But it gives you this roughly 2 orders of magnitude that where you see how the harmonic pieces, like how the anharmonic terms basically start dominating at some point. So there are 2 key takeaways from this. Like as you go to lower and lower Q, you start seeing anharmonic effects dominating over the harmonic effects. The other effect is anharmonic effect, like relative effects of anharmonicity increase as you go to high number of phonons. So these different lines are basically different energies, like going from small energy to high energy. So that corresponds to going to higher number of phonons. And the relative effect increases because for a higher number of phonon, the harmonic term is Q to the 2n, like it's a higher suppression for small q. And whereas an anharmonic term can give you like a term like Q square or Q to the 4. And then that hierarchy between the anharmonic term and the harmonic term, that basically increases as you go to higher number of phonons. And so you get large suppression as you increase the phonon number. Then if you start going to higher Q, so already here the dimensionless factor is 1, and then the anharmonic terms are basically then just giving you very small negligible contributions on top of the harmonic terms. So you already see that there are no basically corrections at this point. And then as you even go to higher momenta, we anyway did not expect any corrections from anharmonicity, because again, for a hard nuclear recoil, the nucleus should not care what potential it sits in. So that's how sort of the anharmonicities go away as you dial up the momentum transfer. Again, I'm going to go through this very quickly. So you can convert the structure factor to scattering rates. Again, I think the same conclusions basically can be seen here. Like as you go to dark matter masses below 10 MeV to a few MeV-ish. So this is showing you a ratio of anharmonic rate to a harmonic rate. You can get like an order of magnitude correction for silicon. These things can be actually very material dependent. So that's one nice conclusion that we also found out. And that's just because the typical single phonon energy of a particular material is different. It's very material dependent. And so if you are setting a particular threshold, your experimental threshold above which you have to generate your energy, then it depends on the material how many number of phonons that you have to produce to get there. If the material has smaller phonon energy, then it requires larger number of phonons, and then the anharmonic corrections are high. So germanium has actually smaller typical phonon, single phonon energy than silicon, and so requires higher number of phonons to get to a particular threshold. So these different colored lines are different thresholds. And so the corrections here can be as big as like 3 orders of magnitude for this mass compared to like an order of magnitude in silicon. So now this can be translated to projections. So again, just 3 events per kilogram year, like super optimistic projections, like background free kilogram year experiment, for example. And we take these different thresholds. On the left is a massive dark matter interacting through a massive mediator. On the right is a dark matter interacting through a massless mediator. On the y-axis is the dark matter nucleon cross section. So for a smaller threshold, which is this line, because you have access to a single phonon or to like smaller number of phonons, you have very small effect, as you can see. But if you increase the threshold where you have to produce a few number of phonons, then you start seeing like these bigger effects, as we learned from the analytics of the perturbation theory picture. So one major caveat here is that like these are, if you look at these cross sections, these are pretty big cross sections, like these 10 to the minus 32, 10 to the minus 30 here even. And if you try to sort of start looking at typical models, like which can have these cross sections at these masses, then for typical models, what happens is like these cross sections would be ruled out, I think, from like some sort of astrophysical constraint or cosmological constraint if you start model building. So from that point of view, if we look at the typical model and constraints, like I would say like these things won't really matter because, and I would say like the harmonic approximation would be okay, like these effects wouldn't really matter because this is too high of a cross section. So that's like one major caveat that we have. And I think with that, I come to my conclusions. So one important conclusion is harmonic approximation seems to be pretty safe to take down to almost dark matter masses of 10 MeV. Then sort of for order a few MeV dark matter masses, there are large corrections that could be possible, as we saw, especially situated around MeV and a few MeVs. These corrections can be strongly material dependent. I think this is an important point that comes out of this simple picture because it's not going to be exactly silicon or germanium that people will use later. It may be some gallium arsenide thing or some other crystal. So it's a usually material dependent property that one needs to look at carefully. And I think the last point is just this caveat that this is happening at relatively high cross sections if you are considering exposures of a kilogram year. Of course, if you consider higher exposures, all these things will come down to lower cross sections. But in a solid state target, already kilogram year is a pretty high exposure to achieve. And so for these typical exposures, I think, and for typical dark matter models, these things will be important only at cross sections, which will be typically ruled out. But that's our analysis, and I think more like sophisticated maybe DFT or some effective field theory techniques will be needed to go to lower momentum transfers. But I think that's an interesting direction. Yeah, but I think that's it. Yeah, I cannot.
I mean, I think we asked them. So.
Yes, thank you.
So the 200 MeV, that's like where you were cutting off. Is that going to be sort of like the first benchmark threshold, or will it be like a little bit more than that? Like 200 MeV was the sort of mega threshold that you were, that was like the largest that you're going up to. Obviously for like
the
even even larger,
I
ones,
can
presumably it's an even more pronounced effect. But is
Yes,
200
yes.
sort of the is that like
I mean,
roughly
no, you can keep going up, but we basically stopped that because then you're like looking at absurdly high cross sections, like 10 to the minus. We wanted to cut the plot off at 10 to the minus 28 because that's where sort of the terrestrial constraints actually hit. Like if you are stronger interacting than that, then your dark matter doesn't even reach your detector.
Yeah, well, there's also, I mean, I can't remember. I think were you there when I came to San Diego?
Yes,
I think so.
Yeah.
But anyways, I mean, the bound that we have is like even, let me think here. The bound that we put is even like here or something in the first paper.
Yes.
So like we say anything about that is ruled out.
Yeah,
Not even
absolutely.
28, it's like, but like you're saying, it's
Yeah.
for like, it's very specifically in this,
Yeah,
like, let's think about realistic models.
Yeah, exactly. Yeah, I mean, realistic models, yeah, that's why I also
Yeah.
like said that caveat, like realistic models, like even here and above is going to be
Yeah.
pretty
But,
much going up. Yeah.
But I think, I mean, but regardless of realistic or models or whatever, these experiments are gonna be built.
Yes.
They're gonna have the thresholds of
Yes,
whatever they
yes,
have.
yes,
So
yes.
like maybe, yeah, would a fair summary of this be to say that like this work and this appreciation of anharmonicity will be most important at the beginning of these experiments? Like,
Yes,
if they're
absolutely.
just starting on as we're going to lower
Absolutely,
thresholds.
absolutely,
Like we
yes.
should 100% be thinking of this, regardless of realistic model.
Absolutely.
Blah, blah, blah.
I
Like
think-
you're
I
still
think
building
so,
the
yes.
thing, you're still taking data and whatever, and
Yes.
so this is very important then. And like eventually, hopefully, if we get down the low threshold.
Exactly,
single phonon, then
yeah.
it'll stop being a subtle.
Yeah,
state,
when
but
you're
this
looking for a
is,
single phonon, then it's like anharmonic effects seem to be only
But
like
for the immediate future, for sure, I mean, we're gonna be deep in
Yes,
the multi-phonon regime.
Exactly,
Yeah.
exactly. And I think like it's going to be interesting to see if people calculate. Yeah, as you said, I think there is like already literature which even I haven't like completely digested yet, like about like these effective field theories of like dark matter coupling to phonons and so on. So there you can like even think about this from like a Feynman diagram. kind of
exactly.
thing,
That's what
like dark matter is coming in and you have some effective coupling with the phonon.
Yeah, I was
And-
talking to, who's at Florida, the new faculty, is it Way, I think? I can't remember. I met him at Aspen briefly, and he was discussing this.
I see.
And yeah, he was exactly saying that there's.
Yeah, so like this would be a one phonon
Yes.
thing, and this would be a two phonon thing, and so if you include an anharmonicity, then you have like three phonon coupling, and then you can have a diagram like this.
Sure.
And so this is an anharmonic coupling basically.
Sure.
So this process they found in Tongyan's paper earlier, they found was actually could get comparable to this.
Okay.
For a single phonon, I think it has to go through some loop or something. So it's suppressed, I think.
Sure.
So all these things at low Q, I think have a very nice Feynman diagram picture.
Yeah, that's cool.
But it just becomes tedious for like for a higher number of phonons.
Of course,
But-
like you said, and then, I mean, obviously.
But anyway, like once you reach there, nobody would care about like higher number of phonons too, because you're just looking at the single phonon thing. But yeah, I think there is a nice correspondence with these pictures. Yes.
Okay, very nice.
Wait, so how much, like you said, the like low momentum transfer parameter space people had already calculated that?
Yes.
So how much of this plot was already calculated? I guess it's not all.
I mean, none of this plot actually, none of this plot. So that was like sub-MEV, like, okay, so what happens is around MEV, neither of the two calculations are really on a
Right,
solid
okay.
footing, so. So here, like,
That's where the
in this,
reference is.
in this, yeah.
Right, or you can't count.
It's not on resonance, it's just on like calculation ignorance resonance.
Yeah,
Just the
yeah.
one place you can't.
So it's like smaller than this,
Uh-huh.
where that calculation was like robust.
Okay.
And, but at least this like logically sort of interpolates to that picture where you start seeing like large corrections. And there they already saw large corrections, so, that's the connection.
And I guess this parameter space would probably be relevant sooner than that parameter space.
Sure, exactly, yeah. Yeah, that's mostly the point of, yeah, as you correctly said, like that was mostly the point of this work, because otherwise, like, for typical models, this is going to be gone, but we will soon be looking at this parameter space, like the first experiments that will be built will be even higher thresholds than that, even 200 milli EV.
Yeah,
is
yeah,
a
that's what I
pretty
was asking.
futuristic- yeah. I think maybe it will be EV first or something, who knows, I'm not completely sure.
Yeah,
but-
and then it'll be huge cross sections, which, yeah,
Yes.
but it's gonna be huge. through
Yes.
the side.
Yes, correct. Yes, absolutely. Yes.
Yeah, I like you did the 1D. I can imagine a 1D oscillator. That's still my ballpark.
Yeah,
Good old fun mechanics, never gets old.
I'm very fond of operators myself. Especially when they're of the latter variety.
Like back when the world was simple.
yeah, I got, like, when we started doing these calculations, I got lost in it for quite a long time. I was like very happy, like this is a very fun, simple calculation.
all day, baby.
Yeah, exactly, yeah.
Number of money bags.